Hi, my name is Bailey Chambliss, and this is my Physics 2212 Lab Number 3, Macroscopic View of DC and RC Circuits. So the purpose of this lab is that using the principles of energy conservation, the loop rule, and current conservation, charge conservation, and definition of steady state, we will predict the behavior of circuits containing resistors in series and parallel. You'll use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. My analysis is that we use multimeters to measure the actual values of conventional current and potential differences in the circuits. And then the results varied slightly from the expected results. This could be due to human error in measuring tools or handling errors. So the fundamental principles that we'll use for this experiment are the loop rule, which says that delta V capacitor plus delta V resistor should theoretically equal 0. The node rule that the current in is equal to the current out. And then Ohm's law that delta V equals Q divided by C, and delta V equals I times R. So charge conservation and energy conservation in series circuits. We predicted that in the series circuit presented to the right, that the current in I1, labeled on the right, and I2 should both equal about 0.02 amps, which is 3 volts, which is the total voltage divided by the resistance of the two resistors, which equals 147 ohms. So this came out to about 0.02 amps. And then in experimentation, we found that I1 was equal to 19.7, which is about 0.0197 amps, and the I2 was equal to 19.6, which is about 0.0196 amps. So these were close to the expected values, but not exactly. And then when we reversed the connections, the sign changed to the negative. And then our experimentation with the ammeter and the voltmeter, we found that when we switched one of the ammeters for a voltmeter, that the current went to 0 and that the voltmeter read -3 volts. This is because with the voltmeter, we have a broken circuit because it's not a component of a circuit. So in our graph of potential versus position, this is what we found. As you can see in the left side, it didn't go all the way to 0 because there was some error. And then on the right-hand side, we just have a graph of the time dependency just in a graph. We expected that round trip should apply, but there was some sort of error. And then the resistance of each element, we found that over the 47 ohm resistor, there was a resistance of 45.5. And then the 100 ohm resistor, there was resistance of about 95 ohms. And then the wire and the ammeter both had 0. So as you can see, the resistance measured was close to, but not exactly equal to, the predicted resistance. And then in our RC circuit, pictured in the top right, our observations were that with the battery, the light bulb will light up and then dim until no light is observed. This means that the capacitor is charged. For the 10 ohm light bulb, this took 12 seconds, and for the 20 ohm light bulb, this took 22 seconds to charge. And then without the battery, the light bulb lights up until the capacitor is fully discharged. For the 10 ohm RC circuit, this took 10 seconds, and for the 20 ohm, this took 21 seconds to discharge. So our results and conclusions, our conclusions are that the loop and node rule are not fully supported, but suggested. This is due to human error. And then RC circuits are dependent on time. Some potential sources of error include inaccuracy of measurement, rounding errors, and timing errors. So our discussion, what if you charged a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. Use an ammeter to measure how long it takes to charge the capacitor when connected directly to the battery and the ammeter. Discuss why the measured time is different from the predicted time. So on the top right, we have our idealized equation. So in the idealized case given by the equation above, removing the resistor from the RC circuit would mathematically predict that the capacitor would instantly reach the battery voltage at time t equals 0. In a real-world experiment, this is not the case. This is not possible. This is because there's still a small amount of resistance from the real battery, the wires, and the ammeter, although in experimentation and in models, we typically ignore this because it's so small. And then in practice, when measuring how long it took to charge, the measured time is longer than the predicted time because of this.